In the previous example, or video, we found the area of a region enclosed by a polar curve situated around the origin. In this video, we're going to look at the area of a region between two curves. So if we had two polar curves and one was on the outside and one was on the inside, we could subtract from the outer, we would subtract the inner to find that region in between. All right, so our definition in this situation says given some polar function r being a function of theta, and we're looking at theta on some closed interval from alpha to beta. So you see that alpha and beta is showing up here. We go from alpha to beta. And same as in our previous example, beta minus alpha needs to be less than or equal to 2 pi. So if we have some positive radius, we'll call it r sub 1, some positive radius in terms of theta, and we know there is a radius in between r sub 1 and the outer radius r sub 2 of theta. The way we can define this is that area A equals the integral from alpha to beta of 1/2 r sub 2, the outer radius, or the outer function squared, d theta, minus the integral from A to B of the inner function squared. So 1/2 r sub 1 squared of d theta. So this is just like when we found the area between two curves in Calculus 1. We had an above minus a below. Here we have an outer minus an inner. And we can simplify that. And we can just say, well, this is going to be the integral from alpha to beta of 1/2. We can say r sub 2 squared minus r sub 1 squared d theta. All right, so let's look at an example. In this example, we're going to find the area that lies inside the circle and then outside the cardioid. So the circle here is going to be r equals 1. And my cardioid is going to be r equals 1 minus cosine theta. So r equals 1 is a circle of radius 1 centered at the origin. And r equals 1 minus cosine theta is a cardioid. And I'll show you what that looks like in a picture here. So here you see my circle. And I'll use color to coordinate this. My circle is r equals 1. And my cardioid is r equals 1 minus cosine theta. And what we are interested in determining here, we want to find this area, the area of this space enclosed by the region. So what we're going to use for my outer polar function, the circle is going to be r sub 2. So we'll say r sub 2 equals 1. And my cardioid would be r sub 1, which is 1 minus cosine theta. So using my formula, which we just set up, A equals 1/2 the integral alpha to beta of r sub 1, sorry, that should be r sub 2, quantity squared minus r sub 1, quantity squared d theta. So we know what our two functions we're going to use. We know what we're defining r1 and r2 as, but how do we determine our upper and lower limits, our alpha and our beta? And that can just be found by setting the two equations equal to each other. So 1 equals 1 minus cosine theta, subtract 1, I've got 0 equals negative cosine theta. And of course, I can divide by the negative on both sides. 0 equals cosine theta. And you have to say, well, where does cosine theta equal 0? And that would be at positive pi over 2, negative pi over 2, and all of their pi k multiples. Okay? So that's where these 2 points, my alpha and my beta, pi over 2 and negative pi over 2, are coming from. So if we wish to set up our area function here, we're going to say that area equals 1/2, that's the integral, from negative pi over 2 to pi over 2. My outer polar function, r sub 2, is just going to be 1 squared minus my inner function, 1 minus cosine theta. That quantity will need to be squared. We've got our d theta here. Okay, so we need to look at simplifying this. And one thing that we can notice is this area region is symmetric. So I can just take my bounds and say, well, I'm going to go from 0 to pi over 2 and then double it. So I've got area equals 1/2 times 2, and that would be the integral from 0 to pi over 2. And you don't have to do this. It's just going to simplify our calculation at the end using that property of integration. 1 squared is 1 minus, and when I square my inner polar function, I have 1 minus 2 cosine theta plus cosine squared theta. So if we look at simplifying what we have here, the 1/2 and the 2 go to 1, so that's going to go away. We have 1 take away 1, that will go to 0. So I have a equals the integral from 0 to pi over 2, negative 2 cosine theta, just gives me positive 2 cosine theta, and then distributing that here, I have minus cosine squared theta. So now this is pretty easy for us to integrate, but again, when we have cosine squared, we often use that double angle. So I'm going to put that in here. We have the integral from 0 to pi over 2 of 2 cosine theta minus 1/2 plus cosine 2 theta d theta, which is the integral from 0 to pi over 2, 2 cosine theta minus 1/2 minus cosine 2 theta d theta. And each of these 3 terms is easy for us to integrate. So this becomes 2, the integral of cosine is sine theta minus 1/2 theta minus sine of 2 theta over 2. And this is, of course, going to be evaluated from pi over 2 to 0. So again, when I go to plug my 0 in, all of those are going to zero out, so we really don't need to worry about that. We have 2 times the sine of pi over 2 minus 1/2 of pi over 2 minus the sine of 2 times pi over 2, all divided by 2. Of course, we would have minus 0 minus 0 minus 0, which goes away. We don't need to worry about that. So sine of pi over 2, that's at 90 degrees, we get a value of 1, minus, that would be pi over 4, minus, that is sine of pi is 0, 0 divided by 2 is 0. So my answer here is 2 minus pi over 4, and that's the exact value of the region of the area bounded by the two curves, the circle and the cardioid.